If you want to explore some different perspectives on these topics,
Okay.
you should check out this YouTube channel called Mindful Moments.
What's that about?
They do these really cool AI audiobook analyses.
Oh, that sounds interesting. Ever try to imagine a number so big that just writing it down would take, I don't know, longer than the universe has even been around?
Sounds like science fiction, doesn't it?
It really does. But it's the kind of mind-bending reality we're diving into today, sparked by George Gamow's book, 1, 2, 3, Infinity.
It's a fantastic source. We're basically looking at how mathematics, sometimes really abstract math, connects with the physical universe we actually live in.
Right. And Gamow's work is great because it unpacks these huge ideas, gives you those aha moments, but without making your head explode with complexity, hopefully.
Exactly. We want to explore these connections in a way that feels engaging.
Okay, so let's start with numbers. Just big numbers. We talk about billions, trillions easily now. But Gamow mentions these Hungarian aristocrats who apparently could barely count past 10.
It seems bizarre to us now, but it really highlights how far our grasp of numbers has come. Think about Archimedes, way back in the 3rd century BC.
Ah, the sand reckoner.
That's the one. He was trying to figure out how many grains of sand it would take to fill the universe. Back then, people thought the number of stars or fish or grains of sand was just, well, incalculable.
So just thinking about it was revolutionary, let alone trying to write down such a massive number. It's hard to imagine a time when even the sand on Earth seemed beyond counting.
Precisely. And this idea of numbers growing unexpectedly large comes up in that classic story about the inventor of chess.
Oh yeah, King Shurram and the wheat grains. That one always gets me.
It's the perfect example of what we call geometrical progression or exponential growth. The request sounded so simple. 1 grain on the first square, 2 on the second, 4 on the third, just doubling each time.
Sounds harmless enough until you get to the 64th square.
And then the number is just staggering.
Yeah.
Over 18 quintillion grains of wheat. Gamow calculates it would take something like 2,000 years of the entire planet's wheat production to pay up.
It really shows how quickly exponential growth leaves our intuition behind.
It does. These huge numbers aren't just mathematical curiosities either. Think about the Tower of Brahma legend.
The monks moving the golden discs.
Exactly. 64 discs, 3 needles, moving 1 disc at a time, never putting a larger one on a smaller one. The legend says the world ends when they finish.
And the time it takes, even moving 1 disc every second. It's something like 58,000 billion years.
Far, far longer than the current age of the universe. It's another way to grasp how simple rules, repeated, can lead to these incomprehensible scales of number and time.
It kind of reminds me of the infinite monkey theorem idea, too.
Right, monkeys randomly typing, eventually producing Shakespeare.
Yeah, the sheer number of combinations, even with just letters, is vast, which I suppose leads us towards infinity itself.
It's a natural next step. And George Cantor's work here was truly groundbreaking. How do you compare infinities?
That's the question. It feels impossible.
Cantor's method was elegant. 1-to-1 correspondence. If you can pair up every item from one infinite set with a unique item from another infinite set perfectly, then the infinities are the same size.
Okay, that makes sense as a rule.
But it leads to some very counterintuitive results, like the infinity of all even numbers, 2, 4, 6, is exactly the same size as the infinity of all whole numbers, 1, 2, 3.
Wait, how? Surely there are only half as many even numbers. That feels fundamentally wrong.
Our intuition struggles with infinity. But using Cantor's rule, pair 1 with 2, 2 with 4, 3 with 6, and so on. Every whole number gets paired with a unique even number, and every even number gets paired back to a unique whole number. No leftovers.
So the infinity of a part is equal to the infinity of the whole. Wow.
That's it. Hilbert's Hotel is the famous thought experiment for this.
Right. The infinite hotel, completely full. But when infinite new guests arrive,
The manager just asks everyone to move from their current room end to room 2 end. So room 1 goes to 2, room 2 to 4, 3 to 6.
which frees up all the odd-numbered rooms. An infinite number of free rooms in a full infinite hotel. Okay, my brain hurts a bit now, but I follow the logic.
It's definitely a mental workout. And you might think, okay, maybe fractions. Surely there are more fractions than whole numbers.
Yeah. Between any two whole numbers, there are infinite fractions.
But Cantor showed you can actually create a 1-to-1 correspondence between the integers and all the fractions too. Their infinities are the same size.
So are all infinities the same size then?
No. And that's maybe even more profound. Cantor proves some infinities are definitively larger than others.
Okay, how?
Think about all the points on a line segment, even just an inch long. The number of points there representing all the real numbers, including irrationals like pi, is a larger infinity than the infinity of integers or fractions.
A bigger infinity. How do you show that?
It involves a clever proof called the diagonal argument.
Hmm.
Essentially, you show that no matter how you try to list all the real numbers between 0 and 1, you can always construct a new number that isn't on your list. It proves that this infinity is somehow denser.
That's incredible. A hierarchy of infinities.
It really reshaped mathematics. And speaking of fundamental numbers, let's touch on prime numbers.
Okay. Numbered only divisible by 1 and themselves, like 2, 3, 5, 7, 11.
They're the building blocks of integers, but they seem to appear almost randomly. Yet their overall distribution isn't random at all. It follows statistical laws, like the prime number theorem.
And Gamow mentions the Goldbach conjecture.
Yes, the idea that every even number bigger than 2 is the sum of two primes. Simple to state, incredibly hard to prove. It's still technically unproven, though widely believed to be true.
Amazing. He notes Schnirelman showed every even number is the sum of not more than, 800,000 primes.
A huge number, but it was progress. That number has been drastically reduced since then. But a proof using just two primes remains elusive for all even numbers. It shows how deep these questions run.
And Fermat's last theorem is another famous example from number theory, right? Took centuries to solve.
Absolutely. These seemingly simple areas hold immense complexity.
Okay, let's shift gears a bit from abstract numbers to dimensions. Gamow uses the flatland idea.
A great analogy. Imagining two-dimensional beings living on a flat surface helps us think about dimensions beyond our own three.
We as 3D beings could look down on flatland in a way they couldn't comprehend.
Just as a hypothetical 4D being could perceive our entire 3D world in a way we can't.
And if a 3D object, like a cube, passed through their 2D world,
They'd only see changing 2D cross-sections, like shifting shapes or lines. It gives us a hint about how we might perceive slices or shadows of a 4D object.
and the fourth dimension, Gamow argues, is time.
Exactly. Events don't just happen at a place, they happen at a place at a time. So we live in a four-dimensional space-time continuum.
Your life isn't just your body. It's like a four-dimensional worm stretching through space from birth to now.
A useful, if slightly strange, image. And this linking of space and time has physical meaning, especially concerning the speed of light. Romer's measurement was key.
Observing Jupiter's moons, right? He noticed the timing of their eclipses changed depending on how far Earth was from Jupiter.
Yes, the light took longer to reach Earth when Jupiter was farther away. That difference allowed him to estimate light's speed. It was brilliant.
Much better than Galileo trying with lanterns on hills. The speed is just too fast for that. Fizeau later used spinning cogwheels, which was more precise on Earth.
These experiments cemented light speed as a finite, measurable constant. And this constant speed is fundamental to understanding space-time geometry.
You mentioned calculating a four-dimensional distance between events.
Right, but you can't just use Pythagoras' theorem like in 3D space. You have to combine space, meters, and time, seconds, carefully. By converting time into distance, using the speed of light, time multiplied by c, but critically, the math involves treating the time component differently, essentially giving it a negative sign in the space-time distance formula. It reflects a different kind of geometry.
Okay, a bit abstract. What does that do?
It's deeply connected to the fact that the speed of light is the same for everyone, no matter how they're moving. This constancy led to the weirdness uncovered by the Michelson-Morley experiment.
The one looking for the ether wind. The medium light was thought to travel through.
That's the one. They expected to measure differences in light speed depending on Earth's movement through this supposed ether, like swimming with or against a current.
But they found nothing.
Exactly. No difference. A null result. It was a major crisis for physics.
So how did they explain it? One idea was the Fitzgerald contraction.
Yes, the rather ad hoc idea that objects shrink in the direction they move through the ether, just enough to cancel out the expected speed difference. It depended only on speed.
And the other idea was time dilation, moving clocks running slow. Gamow's minute eggs on the rocket ship.
Right. If you're on that fast rocket, your 3-minute egg timer seems normal to you. But someone watching from Earth sees your clock running slower, so your A takes longer than 3 Earth minutes to cook. Time itself stretches for moving observers.
So the faster you go, the slower time passes for you relative to someone stationary.
Precisely. Which leads to those hypothetical scenarios, like flying to Sirius near light speed. You might age only a few years.
While decades, maybe centuries, pass back on Earth, mind-bending stuff. And it all hinges on the speed of light being this absolute speed limit.
The cosmic speed limit. You could approach it but never reach or exceed it. And this understanding of space-time sets the stage for Einstein's view of gravity.
Not as a force, but as curvature. Gamow uses the flatlanders on different surfaces again.
It's very helpful. On a flat plane, triangle angles sum to 180 degrees. On a sphere, they sum to more than 180. On a saddle shape, less. The geometry reveals the surface's curvature.
So Einstein's big idea was,
That mass and energy warp the four-dimensional fabric of space-time. Gravity is that curvature.
so planets orbiting the sun aren't being pulled by a force.
They're following the straightest possible paths, geodesics, through the curved space-time created by the sun's mass. Like a marble rolling on a dented rubber sheet curves because the sheet itself is curved.
It's following the shape of space. That's a fundamentally different picture than Newton's gravity.
Completely. It replaces force with geometry. And this overall curvature of space might even tell us if the universe is finite or infinite.
Which is still a big question, right? Whether space curves back on itself like a sphere or goes on forever.
Exactly. Is the universe ultimately finite, even if unbounded or truly infinite? The geometry holds the key. Current measurements suggest it's very close to flat, which complicates the picture, but the exploration continues.
You know, exploring these massive ideas, from immense numbers to the shape of the universe itself, really is a reminder to just pause sometimes. Appreciate the underlying structure and beauty of it all.
Absolutely. That spirit of mindful inquiry, looking closely at the fundamental laws and patterns, is something we actually delve into quite a bit on our YouTube channel, Mindful Moments, and our podcasts. We look at AI audiobooks there to try and foster that deeper understanding.
That makes sense. Gamow's book really drives home how connected math and reality are in ways you wouldn't expect. Thinking about this stuff definitely shifts your perspective.
We hope exploring these concepts has sparked some curiosity and maybe a few of those aha moments for you listening.
Definitely. If you enjoyed this and want to explore more fascinating topics, please do subscribe and maybe share this with someone else who enjoys thinking about the big questions.
And if you want to read the original source, we put a link in the description where you can find George Gamow's 1, 2, 3, Infinity. It's a classic for a reason.
So here's a final thought. We've seen our everyday intuition about numbers, space, and even time kind of breaks down at cosmic scales or extreme speeds. It makes you wonder, what other basic assumptions that feel totally solid right now might actually need a rethink for us to truly get a handle on the universe?